Our speaker today is Lode Pollet. Lode is a professor for theoretical nanophysics at LMU in Munich, which I believe you can see in his background here. In his research, he studies the physics of matter from first principles. He is an expert in the development of quantum Monte Carlo algorithms and applies these tools to the study of strongly coupled many-body systems, disordered systems of bosons, as well as ultra-cold atomic systems. In his talk today, he will explain the use of a new and emerging tool in this field. He'll speak about the use of machine learning in the characterization of phase diagrams. Lode, please start whenever you're ready.
All right, thank you. Let me go to screen sharing. All right. No, I don't see my own screen. All right. And so I hope it's fine.
Perfect.
Okay, so good afternoon also from my side. Thanks to Philip for the invitation and for the very kind introduction. What I would like to talk about today is the tool in the field of machine learning that we have been working on in my group for a number of years now. It is about phase characterization, so it's about mapping out phase diagrams. And by doing so, hopefully learn new things, so discovering new phases of matter. And the title is slightly provocative because I claim that what we do is at the same time unsupervised and interpretable, which I will explain during this talk. I should say that the heroes of what I'm going to say are my postdoc, Curl Yu, who's still in my group, and former PhD student Jonas Greitemann, who unfortunately left academia, and this line of research has been picked up by new students, Nihal, Nico, and Mark. And if you are interested in reading more about what I'm going to say, here are some references for you. Yes, and if you have any question one way or another, let me know, and I'll be happy to answer anytime. Okay, so let's get started. So we are interested in the classification of data, and what we are going to use is a variant of a support vector machine, which in its simplest formulation is the following problem. So given two sets of data, say in green and in red, labeled with the label +1 and the label -1, find a way to separate them. So find a way to classify them by defining this hyperplane, Wx minus rho equals 0. And this is done in such a way that you try to maximize the distance to the nearest points of each phase. Okay, so you try to define this hyperplane, and these algorithms will, based on training data, give you values for this W and this rho. This function is called the decision function, so it's 0 exactly on the separator. It's positive for, say, class +1, and it's negative for class -1. Okay, and as I said, it tries to maximize this margin. Data that are exactly on the margin, they are called the support vectors, and they determine the properties, ultimately, of the decision function. This constant rho, in its simplest formulation, is a kind of a normalization constant to satisfy that this is +1 and -1. Okay, now, in this formulation, the support vector machine would be very restrictive in its use. Fortunately, you can relax a lot of the hidden assumptions. So first of all, such algorithms are rather robust against misclassified data. So if you are in a situation in which a lot of data are initially misclassified, so you have like these green squares here below the line and some red dots above the line, it will still work, but you have to introduce some slack variables. Now, the main drawback of what I said so far is that the hyperplane is really a hyperplane. And what gives support vector machines their ultimate power is the fact that you can use kernel trick. So it is possible to find separations that are curved, yeah? that they are not hyperplanes. And the way that this happens is that, at least formally, there is a mapping from the input space to some feature space, and this mapping is phi. And whereas you have a curved line separating the blue and the red data shown here, in this feature space, there is a hyperplane separating them. And this is possible. And there are some very mild assumptions under which this kernel has to work. And what is important is the choice of the kernel function. So how well it will work depends on the choice of your kernel function. So for instance, you can take a linear kernel. This is what we had before, or a polynomial one. So of great importance to us is the quadratic kernel. But you can also take some Gaussian functions and so on. And so what you see here is a quadratic function that is perfectly capable of separating the two data, but a linear function will never be able to do so. Interestingly, this mapping does not need to be known usually explicitly. And usually you will go over from a physical space to a feature space which has a much higher dimension. However, none of this is important. The only thing that matters is that one is able to compute these products or essentially these kernel functions acting on training data and data. Okay, so what we will use is always a quadratic function later on. Now, I should say, as a kind of a disclaimer, so the problem we are trying to solve here is about classification of data. So it starts from the fact that you already have good data. And I would agree with you if you say that getting good data is at least as hard, if not harder, than classifying the data. And so this problem that we are looking here is about analyzing data. It's about looking at symmetry breaking. It's about perhaps detecting critical points, perhaps detecting dynamical information. Unfortunately, topological order, we don't know how to do it. But it starts from the premise that you have good data. And if your data is not good, it will not work. And how to get good data is simply not addressed here. Okay. Okay, now you may ask, but once you have good data, what is so difficult about getting a phase diagram? Isn't it just simply, if you have a ferromagnet, you look at the magnetization. If you have an antiferromagnet, you look at the staggered magnetization. What's so difficult about it? Well, it turns out that in many materials, and especially in frustrated materials, the order can be very complicated and hidden. And it's not obvious at all what type of order you can have. So here is an example. So you have here a material, gadolinium, gallium, garnet. And its lattice structure essentially consists of two interpenetrating Kagome lattices. And it turns out that you have some kind of hidden quadrupolar order, namely, this is a loop that you have to imagine here that is a bit curved. But if you look at the spins, the 10 spins that are here drawn in orange and green, it turns out that they form quadrupolar order. So there is, in other words, a director field that defines the planar orientation of these spins. And so you can write this vector L as a sum over these 10 spins. And the order that you see will be quadrupolar. And so it is the tensor product of L with itself that will pick up the order. And this is hard to find. And these are the kind of things that we would like to automate. The history of this field goes back roughly about 5 years. So the first papers talking about discovering phase transitions are by Lei Wang, discovering phase transitions with unsupervised learning. That those apply to the Ising model using a principal component analysis method. A paper by Karaskia and Melko on machine learning phases of matter also applied onto the Ising model, Ising-Gauge model, using a CNN and supervised learning. And of importance for us is a paper by Ponte and Melko on kernel methods for interpretable machine learning of all the parameters. And this paper in particular is the starting point for what we have done. And also here it was applied to the Ising model, Ising-Gauge model, and it also used CNNs and supervised learning. In the meantime, there have been many papers, and I've tried to compile a list of recent developments, and I hope that if you worked on it, that your name is mentioned, and if it's not, then I apologize in advance. But probably I missed some more, but definitely this is a hot field of research at the moment, attracting also researchers from different fields. And so I'm sure there is more to come in the future. Okay, now let me mention in more detail the paper by Ponte and Melko. So this is about the classification of a classical ferromagnet, so a classical 2D Ising model. In the classical Ising model, you have a 2D square lattice, and on every lattice point, you have a classical spin degree of freedom. That is, this variable sigma can either point up or down, labeled here by values +1 or -1. For positive values of J, you see that you will minimize the energy if all the spins point in the same direction. So in other words, the ground state will be a ferromagnet in which all the spins point either up or all point down. There are two equivalent ground states. At high temperature, entropy will win, and there will be essentially no correlations between the values of the spins, and you will get a disordered configuration typically. So in other words, a paramagnet. So the 2D Ising model has a phase transition from a paramagnet to a ferromagnet, a Z2 transition, as a function of temperature. And what you see here in the plots are typical snapshots, say, from a Monte Carlo simulation. So on the left, you see a ferromagnet. Yeah? So most of the dots are black, and there are a few white dots. And on the right, you see something that is disordered. You have probably as many white and black without correlations between them. And in the middle, you see like large domains of white and black regions. So you get large domain walls. This is definitely in the critical region, close to the phase transition. Okay, so for a human, this classification problem is rather simple. Namely, in the ground state, the magnetization is 1 or -1, but the magnetization squared is always 1. And at high temperature, the magnetization is 0, and magnetization squared is also 0. Okay, so in this sense, that's what you think would be a very good classifier. And does the machine also learn this? The answer is yes. So Ponte and Melko used an SVM in the sense that I described above. And it turns out that the decision function, this function D, can be written as follows. So you have your spin vectors sigma A and translated sigma A plus X by an amount X, sum over all the lattice sites and sum over all the translations. And then you have a constant Cx that the machine will determine. And you have an offset rho. Yeah? So given enough training set data, the machine will define optimal values for these structure constants Cx, A, and this rho. Now, we as a human, we know the right answer. We know that the magnetization squared is a perfect order parameter. And now the magnetization squared can be written as the integral over the spin correlation function, sigma sigma. This is exactly this form. Yeah, we know that coefficients are then essentially always 1. So you would expect that indeed this can pick up the transition and that these constants are essentially just constants. Now, these numbers are constant, there is no behavior in them, because then the decision function reduces to m squared. And this is indeed what is seen. So what you see here in this plot is that the machine has learned that these constants Cxa, which are plotted, are just constant. They always take the same value. If you look more carefully, you will see that at the origin there is a slightly different value. As far as I know, this was discarded in the paper. However, there is something in it. We will come back to this later. Okay. What one means with the statement that SVMs, support vector machines, are interpretable is essentially this, namely the result of the SVM, which is this decision function. These constants C can be interpreted, can be given a meaning that is known to us as physicists. And so in other words, we can learn order parameters just by looking at the decision function. All right, I see something on the chat. What's the advantage of support vector machines over, let's say, artificial neural networks in classifying quantum phases? Okay, so thank you for the question. So first of all, quantum phases at the moment, we have not looked at them. We are currently working on them. I cannot say much. Now, in general, and I will come back to this later, support vector machines are argued to be easier to interpret than neural networks, in the sense that it's easier to interpret these, the answer, these constant C in this case, for us as humans. You will see examples of this. So they are generally considered to be easier to interpret. The drawback of this is that they are generally considered to be problem specific, whereas neural networks typically are more universal. Okay, SVMs are supervised learning. Most of the CNNs that I know are also supervised learning, but we will come here to a thing that can be unsupervised, which I will explain. Okay, so in other words, if you know more, if you're doing neural networks and you want to interpret your output, then you have a number of strategies. Yeah, you could look at the output neurons. So in this case, you would definitely be successful with classifying an Ising model, and you would have as output neurons something that says that magnetization is 0 and something that says that the magnetization squared is 1. This would perfectly be possible. Other approaches would be based probably on autoencoders. This has also been tried in the literature. But I would like to convince you that for the problem of phase classification, what we do here is probably better. And so I hope to convince you of this in the next slides. But you have to move away from the Ising models. For Ising models, everything works and everything is known, and it's kind of simple. Okay, so the situation as I described it till now is however not very satisfactory, because you have to do training on data that has already been labeled. So in other words, you want to learn the difference between apples and oranges. But before you can do that, a teacher has to say that this is an apple and this is an orange. And then if you study hard, you will be able to see the difference between an apple and an orange if you are given a new data set. But somehow this is not very satisfactory, because what you would like to do in physics is just look at the data and try to see phases that we have not seen before and that we have not learned before. The drawback of such an approach is that the teacher must know what phase it is in advance. He must know that already you can have an apple in this system, you can have an orange here. But what if the order is so complicated that no human has ever thought about it? Yeah? So we would like to get rid of this supervised learning. So we would like to get rid of this idea that you have to learn first based on data that has been correctly classified before. Yeah? So in other words, if you encounter a kiwi, you would like to see that this is different from that and pick up the properties of a kiwi. And I claim that this will be possible. So how is it possible? Well, actually, you have to look carefully, and it is possible to explain it on the basis of the Ising model again. So namely, if you look at what magnetization is doing as a function of temperature, at high temperature, it's always 0. And when you reach the critical temperature, either it will go towards +1 or it will go towards -1, depending on the fluctuations that determine which way the spontaneous symmetry breaking will. Now, if you would map all these points onto their magnetization value, you would put them here at 0. Those would be essentially all 1, and those would be -1. Now, if you would add like arbitrary phases to these numbers here, you would have a 2D classification problem, and all the high temperature points would map onto the origin, and the ordered phases would all map onto a circle with modulus essentially 1. Okay, so what I'm saying is that the phase classification problem is very special. Namely, all the points of the disordered phase map onto the origin. And so in other words, if you have to find a classification between the origin and the circle away from the origin, it's clear that all the points at the origin, they are support vectors for the disordered phase. So in other words, the bias, which is usually just a normalization parameter in a classification problem, has a physical meaning in the issue of our phase classification problem here. Namely, if you want to see the difference between a point here and a point here, the bias should be +1 or -1, exactly. Okay, and this holds for any two phases where one phase is a disordered phase of the other one. So if this one has a higher symmetry than these points, this will work. Yeah, so if these are a subgroup in symmetry of what you have here, this property will work. This is now important because now you can make a big step and you can get rid of the training initially. So all you need to do is look at different temperatures, and every time you look at the result of the SVM and you compare 2 points and you look at the bias, this rho. And if this rho is 1, then you know that they are not in the same phase. And if rho is quite different from 1, then you know that they are in the same phase. And by extending this, you can do now a scan over the whole phase diagram. You do for every parameter point a pairwise SVM, you look at the values of this rho, and you will pick up the topology of the phase diagram. Okay, so this is essentially what we do. So you look at the bias between 2 points A and B, and you check what's going on. If this value rho is much greater or much smaller than, much greater than 1 or much smaller than -1, then it's safe to conclude that A and B are in the same phase. If this value is about 1 or -1, then a phase transition takes place. If it's +1, A will be disordered, B will be ordered, and vice versa for the other sign. This is anti-symmetric in the indices. If, however, the value is somehow between -1 and 1, say 0.5, then essentially they are not directly comparable. So the idea of a subgroup doesn't hold. Okay, and based on this property, you can now draw lines between points that are in the same phase, and you will identify graphically components, regions that have the same symmetry. And this is how we can make it unsupervised. Yeah, so we will detect components, areas in parameter space that have the same property before having analyzed further what exactly this property is. And that's how we proceed. So let me give an example of this. So this is a tailored model in which we have 3 phases. So we have an isotropic phase with O3 symmetry. We have an uniaxial symmetry, uniaxial phase with cylindrical symmetry, and we have a biaxial symmetry D2H. How we generate the data here is not so relevant. Yeah, this is a tailored model based on gauge theories. And we compare 4 points: the origin, this point here, and this point. So 0, 1, 2, and 3. And every time we look at this value of rho, and the 2 columns correspond to different types of regularization, dealing with misclassified data, but essentially it will not matter. And you see, if you compare 0 and 1, that the value of rho is essentially 1. If you compare 0 and 1, it's 1. 0 and 2, it's 1. 0 and 3, it's 1. And indeed, every time there is a phase transition between these points. Between 1 and 2, there is also a phase transition. Between 1 and 3 as well, but the value is 1.27. Between 2 and 3, it's obviously not 1, it's 8. And you would conclude that 2 and 3 are in the same phase. Yeah, so based on the values of rho, you could then do the following. Yeah? So instead of taking just the 4 corners, you now do a scan of the whole parameter phase. You look at rho. If the values are the same, you draw a line. If they are not the same, so if rho is 1, you draw no line. If rho is quite different from 1, you draw a line. Then you have to add a little bit of technical detail with a weighting factor, but it doesn't really matter much. And the result of this is, from this analysis, is that you see 3 components. Yeah? So you see a component up here, you see a component up here, and you see a component up here. Yeah? And just by doing this, I learned the topology of the phase diagram. I learned that there are 3 phases, but I don't know the order parameters yet. Yeah? I don't know yet. Well, I do know that this probably has the highest symmetry, because I know the values of rho are +1 or -1. But I have not figured out that this is uniaxial and this is biaxial symmetry. But I have made a step towards unsupervised learning. I have not seen these data before, and I could pick up these components already. Okay, and you can also replot this. So there is a way in graph theory based on the so-called Fiedler vector to visualize this. And this gives you the same information as before. And you get these 3 components in red, green, and purple. Okay, so essentially this is what I wanted to say. So what we have said is that the SVM can become more universal. It is interpretable, but it becomes more universal in the sense that it becomes more unsupervised when equipped with this graph analysis. Okay, what are the advantages of this scheme? So in what we will see below, you don't have to cook the order parameter, you will be able to read it off. So you don't have to guess the order parameter as you usually have to do. You will be able to read it off if you use our tool. Chances that you miss an order are reduced if you do a systematic scan over parameter phase. This kind of graph analysis will pick up any component that has different local properties than another component. And perhaps this is a faster way of doing the analysis when you have many parameters. Okay, now the most important property of what we do is actually what is called the tensorial kernel. Namely, we need a way of expressing all possible order parameters for classical models in this case. So, and the way that this is done is as follows. So you have your original lattice, and we will define a unit cell, which you see here. And this is what we call cluster averaging. So we will average the whole lattice so that everything is reduced to one unit cell. It doesn't have to be a physical unit cell. It is just a unit cell that you choose. It could be 2 physical or 3 physical unit cells. And then we are going to define tensorial tensors essentially based on these spins. So we are going to have, in this case, 8 spins. Each of them may have components X, Y, Z, and we just built a tensorial basis like that. And now any local order parameter can be expressed in this tensorial order, in this tensorial basis with unknown coefficient C alpha. And so our feature mapping, this phi is exactly the mapping from all the Monte Carlo spins on the lattice towards this tensorial construction for one unit cell. Now, in our case, this reduces actually the amount of information one needs to store substantially. I don't want to go into the math. So the formula that you see here, it may look trivial, but it is really the key of why everything is working so well. Because any local order parameter can be written in this construction. The tensorial kernel we do is the mapping from the original spin configuration onto such tensors, and then we take a quadratic kernel, and it follows then that the decision function is essentially these phi with structure constant c and the rho. And so all that the decision function will do is, or the SVM will do, is optimize these coefficients c and rho. And those c's are essentially averages over the tensors. So if you have a tensor of rank 1, to define a ferromagnetic order, you just need one spin. And so you can just sum over the whole lattice, sum up all the spins, and you will have it. For an L order, you need to do it on 2 sublattices with a minus sign. But it becomes far more complicated if you have to look at quadrupolar or octupolar order. And this is what we're going to do. So this is essentially the whole setup. So we are getting from SVM a decision function d. Essentially, we're going to get coefficients c, mu, nu, and rho. Whereas usually rho has no meaning. It's a global shift for normalization. In our scheme, it does have a meaning. That is very specific to the problem of phase classification. Namely, we first analyze this bias parameter rho. It will give us the topology of the phase diagram, and it will give us an idea of what phase is more ordered than what other phase. After we have done this, we will analyze the symmetry properties of each phase individually by analyzing the structure constant c, mu, nu, from which we will be able to extract order parameters or local constraints instead of spin liquids. Okay, and this is the whole scheme that works. And so this was now applied to a number of systems. So they were all classical spin models so far. So we applied it on the classical XXZ model on the pyrochlore lattice, the classical Heisenberg model on the Kagome lattice, and on models relevant for the Kitaev materials. And so for the first two, we essentially reproduce everything that was known so far. For the third one, we discovered some new phases. So let me see, how am I doing in time? Okay, I think I'm half an hour in the talk, so I still have some time. So let me choose and show you what we get for the pyrochlore system. So what you see here is the phase diagram for the XXZ model on the pyrochlore lattice. And you get a number of phases. So when you change the anisotropy, so the XXZ is meaning it's an anisotropic Heisenberg model in which Jx, Jy are different from Jz. Written here in quantum notation, but it's definitely just a classical system. You see that in the ground state, you can get an ordered phase when J plus minus is strongly positive. You can get spin ice physics here. You get an ordered nematic phase here, and you can get at minus 0.5, you get an Heisenberg spin liquid only at this point. These full lines are phase transitions, the dashed lines are crossovers, and so you see that there is a paramagnetic region. There is something in which you can call it a spin liquid, which then goes over to the nematic phase here. And this is what we're going to see. So the phase diagram you see here was computed by Taï-Fumier et al. In collaboration with Ludo Joubert, Nick Han, and Nick Shannon from the University of Okinawa. And these systems are believed to be, or at least spin ice is believed to be relevant for polonium titanate and dysprosium titanate. And here you see the pyrochlore lattice consisting of corner sharing tetrahedra. And our goal will be to kind of reproduce this phase diagram. This is more than what we had before because spin ice is not an ordered phase. This is a local constraint, namely per tetrahedron, you will have 2 spins pointing inward and 2 pointing outwards. And this has to be satisfied for all the tetrahedra. And such a construction is not the same as a local order parameter. It's just a local constraint. Okay, our first step is to define our tensorial basis. Namely, what we have to do is, in this case, cluster average onto one tetrahedron. So we average the whole lattice onto one tetrahedron with just 4 spins. Okay, and now we will be able to discuss everything based on rank 1 and rank 2 properties. So if it's rank 1, we have 3 degrees of freedom per side. So that means it's a 12-dimensional matrix. For rank 2, of course, it's 3 times 3, and you will get ultimately 144 times 144 as a matrix for the CMU. Okay, so as Nick Shannon likes to say, this is a competition between the machine and humans. In this case, the humans definitely have a head start, so let's see what the machine can do. So we play our game and we start with analyzing the phase diagram in the same way as I've shown you for this toy model, but now for this XXZ pyrochlore model. And now we start with the rank 1 TK-SVM. And what we see is that there is one component here which is very distinct from the rest. So, and if you look at the phase diagram we had before, this was an ordered in-plane antiferromagnet, but there is no structure seen in the rest. If you go to rank 2, all of a sudden, so we no longer look at this single component here, but now at rank 2, looking at quadrupolar order, all of a sudden you see that there is structure here. You see all these different components emerging. I still don't know what they are, but I just see that there are different regions in this phase diagram that are different from other regions. When I continue to rank 3 and rank 4, this picture doesn't change. So everything can be explained with rank 1 and rank 2. Looking at the value of the rho, I know something about the order of the phases. And when I label these different components as I've identified them from the graph analysis, I would call them 1, 2, 3, 4, 5, and 6. And I would see that 1 is the most ordered phase and 2 is the most disordered phase. So 2 will be the high temperature phase essentially connected, and 1 will be an ordered in-plane antiferromagnet. Okay, and I can learn something that 4 is more ordered than 3, but that there is, for instance, no relation between 3 and 5. And this number here is 0.5, so 3 and 5 cannot directly be compared. Okay, so I know something of the disorder hierarchy. 2 is the most disordered, 1 is the most ordered, then 6 is the most disordered, and then it essentially splits. There is a path 5, and there is a path 3 and 4. I don't know yet at the moment the symmetry of these phases. Yeah? So what is written here, that this is a correlated O3 paramagnet. This is a trivial O3 paramagnet. This has cylindrical symmetry, easy plane. This is easy axis cylindrical symmetry. I don't know yet at the moment. Or that this is just C1H, or I don't know at the moment. I will learn this from looking at not rho, but a constant C mu nu. Now let me do that. So let me compare the phase 1, which was my antiferromagnet, with infinitely hot temperatures. And analyzing this CMU nu, they look as follows. So it's a 12 by 12 matrix. And you see that most of it is 0. And then there are entries that are constant. Yeah? So I normalize them to 1 on x, x, and y, y. And that for every spin. Yeah? So you see the 4 spins of a tetrahedron, and each time there is a x, y, z component of them. So in other words, mathematically, this can be written in the following way. Yeah? So an x, x, y, y for every block can be written as delta AA prime 1 minus delta AZ. So delta AA prime says it should be diagonal, and there is nothing on the z, so it should be subtracted. Or if you write it in physical terms, this is an sx squared plus sy squared for every spin individually. And sx squared plus sy squared, this is indeed the in-plane. So m perp component squared. So in other words, this indeed corresponds to an antiferromagnet that is in plane. Yeah? And by looking at such matrices, this is how we infer the symmetry and the properties of the phases. And this has now to be done, this type of analysis for each one of the phases, and it gets more complicated. And because the rest of the figure has to be done at rank 2, and then the matrices are 144 times 144, and that's more complicated. But if you do so, you will learn all the properties you need to do. You need to know to learn the phase diagram. So you will learn that phase 4 has symmetry C2H. You will see that 5 has spin ice constraint, namely in the z direction 2 spins point inwards and 2 outwards. So this, you will see this, that the sum of the 4 z components is 0 in phase 5. For phase 6 here, the classical Heisenberg model persisting up to 0 temperature, you get such a constraint for x, y, and z at the same time. And in 3 and 4, you get such a constraint just for x and y. And all of this can be learned. So also the fluctuating fields here of the biaxial nematic can also be learned. All of this can be learned. Yeah, so this is a big success, and we caught up with the humans. Yeah? So the machine has learned all the information that the humans have deciphered, but it could probably do it faster. However, it still needs good data from the humans. Now let me skip over the Kagome. Essentially, we reproduce everything that is known. Essentially, the quadrupolar order that John Chalker came up with in '92, and then later developments by Zhytomyrsky and collaborators for octupolar order. All of this has been reproduced. Also, some tiny order at the dipolar channel. So a root 3 order space has also been found with tiny moment. And in the final minutes, let me say something about Kitaev materials. So these are very anisotropic models. So you have now a honeycomb lattice in 2D, and you have essentially different types of interactions depending on the type of bond. Yeah, so every neighbor has so every site has 3 neighbors, and you see blue, red, and green bonds, and on each one of them you get either XX, YY, or ZZ interactions, fully anisotropic. Okay, now the quantum model, written as such here, this Kitaev model can be solved exactly. And this is what Kitai famously did using Majorana fermions and a Z2 gauge field. Now, unfortunately, on the quantum case, we cannot say much at the moment, but this is very rich. Namely, it can harbor gapped spin liquids with abelian topological order if you are in a case where Kz is much greater than Kx and Ky. And even more interestingly, if you add a magnetic field along 111, you can actually have a non-abelian Ising type topological order. And what I found also very surprising is that theorists have said, well, there are components, such as the iridates and the rutinates, in the edge sharing geometry that can almost realize such anisotropic interactions. There are, of course, some rest terms. And it is currently believed that one of those here, namely ruthenium trichloride, is very close to such spin liquids. It's considered a proximate spin liquid. And there was a lot of enthusiasm in the field in around 2018 and still going on, based on a, let's say, controversial observation of a quantized half-integer thermal Hall effect and intermediate fields, which would essentially prove all of the above. Now, we looked at it from a classical point of view first, because we think a lot of information can be learned. And we look first not just at the Kitaev model classically, but we add the main source of anisotropy, which is this gamma term. So on such a gamma bond, say ZZ, you now have an off-diagonal matrix in the other components. So if this is gamma is Z, then alpha and beta would be X and Y. Yeah, so it still rotates. And we do the same analysis as before. Yeah? So a lot of Monte Carlo, careful annealing in temperature, parallel tempering, getting lots of data points. And then we do our graph analysis. And after that, look at the symmetry of the phases. And it's way too complicated to explain all of this now. However, what we learned for just this gamma K model in zero magnetic field is we reproduced Kitaev spin liquids. We also found gamma spin liquids in the case where the K interaction is 0, and we found new phases. So what is new is that this phase is new, this S3 cross Z3, which has 18 time unit cell, and this one, which is the antiferromagnetic equivalent. And we could also find explicit formulae for the gamma spin liquid, so for the constraint that governs this gamma spin liquid. And I don't want to explain all of this now. I just want to say, if you add a field, you get even more phases. So all of these you see here. And what is nice in what we do is that you get explicit expressions for the order parameter. So if you compare this, our phase diagram with the one from the group of Young Beckham, you will see in their paper that they indicate how many atoms are in a unit cell, and then they will show the static structure factors corresponding to this, but they don't know always the precise formula for the order parameter. So what they write here as this 18 could at least in principle correspond to our S3 cross Z3 because it also has a unit cell of 18 sites. Okay, and the symmetry of this S3 cross Z3 is rather complicated, and I can explain if you have questions, but otherwise I'll skip over it now. And then, yeah, we continued working along this. So we added more interactions because the Hamiltonians of these compounds are essentially totally unknown. So we add Heisenberg ferromagnetic interactions, and then we see that this S3 cross Z3 can actually be stabilized to some extent. You find zigzag phases, which is believed to be the ground state in zero field of alpha ruthenium chloride. But you can also get something new, which is a zigzag stripy phase nested here, which this is also new, was not seen by anyone else. If you add next nearest neighbor Heisenberg interactions, you will always stabilize zigzag. And if you have a term, this gamma prime, which accounts for tetragonal expansion for positive gamma or compression for negative gamma, you may also stabilize the zigzag phase. And so we believe that this is what's going on in alpha ruthenium chloride, that you have tiny amounts of stabilizing zigzag factors. Otherwise, you would have found something else. Okay, if you're interested in what we do, the code is essentially open source. So there is on GitLab a project TK-SVM open source, and it contains for most of the papers we worked on open source codes that you can have a look at. Okay, we wanted to organize a summer school in Munich last year already, but it's been postponed by 2 years now due to the coronavirus on machine learning and physics. And so if you're interested, stay tuned. We will hope to do something in 2022. And so with this, I'd like to conclude. So what I presented you, our TK-SVM is a tool in which we try to make the SVM not just interpretable, but also universal and unsupervised. It can capture all local order parameters and local constraints. It is interpretable, so we were able to learn order parameters explicitly. It's unsupervised because of the graph analysis. Of course, you must have good data, and so far it must be from classical models. We are still working on quantum models. There are lots of complications with quantum models that you don't have classically. And I believe that there is no other tool that can give so much information by just looking at data. Yeah? So it gives you order parameters as opposed to cooking up, and they can be really complicated. It was applied to all complicated standard models of classical spin liquids, pyrochlore, Kagumi, and Kitai at the moment. And we've been able to identify some new phases with highly complicated order parameters and some explicit expression for constraints. Okay, so with this, I'd like to thank you for your attention. If you have more questions, I'll be happy to answer. I go to stop share.
Wonderful. Thanks a lot, Lode. That was really, really interesting. So if people have any questions, then please, I would ask you to raise your hand, and then I'll try to unmute you. Or you can also keep writing questions in the chat window if that's what you prefer. Okay, maybe let me start then. I was curious about, so when you started speaking about the your tool, you spoke about these unit cells that you need to choose for your algorithm. And you said that the size of that is essentially arbitrary. So I was curious, what if you choose it too small? Wouldn't you be able to sort of miss very long range correlation or very long range structures that could show up as an order parameter, like these loops that you used as an illustration at some point?
Yes, so far the choice of the unit cell is not automated, it's done by a human. If you choose your unit cell too big, it cannot hurt, you will just get more copies of the same order. Of course, your size that you can simulate is limited. Yes. So you will have less statistical averaging. If you choose your unit cell too small, you will not pick up the right order because you will end up with some domain walls, maybe other defects. This we don't get rid of. So if you have large unit cells, like in the Kitaev case, where if you have a unit cell of 18 sites and the system size you simulate is 72 times 72, 72 times 72 times the number of spins, this is a huge amount of spins, but still it's only 4 of those unit cells. And of course, the choice of 72 then matters again. Yeah, and these things, they are not automated. They still depend on the human.
Yeah.
This is yeah.
That makes sense. But you're saying it's safer to choose a big one, even if you have to deal with many copies and lots of complexity, than choosing it too small and potentially missing something.
I still think the safe strategy is to start small and bigger and see what's going on. Commensurability issues, they will be there, and I mean they're more. I mean, I think they're more a problem of how you actually do the Monte Carlo simulations than the analysis afterwards. Because once the data is not good, the analysis can be as good as you want. It will not be better than the data. Yeah. And this, of course, cannot. This is currently not. I would say it's not solved at the moment. So the hard part of how to get actually good data is definitely not solved. Yeah, unfortunately. So. Have no local order in this topological phase, way to construct to determine topological invariant from scratch. Maybe. So currently, no. I mean, currently we don't know how to do this. So like Wilson loops, we definitely don't know how to do it, and I don't really. I mean, in this scheme, it would be very difficult to do it. But maybe there is another way of looking at these things that makes it possible. But currently no. No, so sometimes there are like simple SPT phases, but they may have emergent symmetry, and then the emergent symmetry can be picked up. Sometimes this is possible, but in the most general case, I don't think so at the moment.
Okay, any other questions? If there aren't any, then thanks again very much, Lode, for a very, very nice talk. And thanks again to everybody who joined, for people who asked questions. And that's it for today then. Talk to you again next week.
Okay, thanks for having me.
Bye-bye.
If you have more questions, feel free to drop an email anytime. Okay.
That's good. Thanks a lot. Bye-bye.